Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIUA campus. In this video, we will discuss discrete Fourier transform and some of their properties. Okay, let's first discuss what is the difference between discrete time Fourier series and discrete time Fourier transform. The Fourier function is unique. What does it mean? It means that no two same signals in time. For example, you have a two same signals in time, but they will not give the same function in frequency. So it means that if you have a two signals in time, whenever you take the Fourier transform or the Fourier of that function, then you will get different functions. So discrete time Fourier series, when we use, is a good analysis tool for systems with periodic excitation. So it is good for when the signal is periodic, but cannot represent an aperiodic or non-periodic discrete time signal for all time. So it means that it can uh, be Fourier series is possible for aperiodic as well, but for not all the time instant. So for that we prefer discrete time Fourier transform for a discrete type of a signal. So DTFT, discrete time Fourier transform, can represent an aperiodic discrete time signal for all time. Its development follows exactly the same as that of the Fourier transform for continuous time aperiodic signal. So the discrete time and Fourier transform and the continuous time Fourier transform development is almost same for the aperiodic signals. So overview of some symbols just to notify the difference between discrete and continuous time. Usually for discrete time we use x of n, and where n is variable, and capital N we use for the period, and continuous frequency we use omega, the symbol omega, capital omega. For discrete frequency we use a symbol k. So omega k equals to 2 pi k over n, right? And for continuous time x of t, we represent using continuous time signal as x of t, and t is variable here. And for the period, we represent capital T, and omega or ohm, you can say, the symbol, and discrete frequency k. Now let's summarize some difference between the different continuous time Fourier transform, discrete time Fourier transform, and so on. So what is discrete time Fourier transform? So what are the key characteristics of the feature? In discrete time Fourier transform, it is discrete in time. It means that they have a discrete values in time, and it is valid for aperiodic in time. So the signal will be aperiodic in nature. And whereas whenever you take the Fourier transform, the resultant signal will be continuous in frequency, and there will be a periodic in frequency as well. So discrete time Fourier series, it is discrete in time. However, as it is Fourier series, so it is periodic in time and discrete in frequency. So the output, whenever you take the Fourier series, the resultant frequency will be discrete, whereas in Fourier transform, the resultant frequency will be continuous. So this is different, and periodic in frequency, right? The frequency will repeat. And continuous time Fourier series and continuous time Fourier transform we already discussed, so you can read them. Okay, this is a summary of the equations, synthesis equation and the analysis equation, which can be used to find the discrete time Fourier transform and the inverse Fourier transform. But to find the discrete time Fourier transform, x of e j omega equals to n equals to minus infinity to infinity, and this is your x of n given signal e minus j omega n. And to find the inverse Fourier transform, you will use this equation 1 over 2 pi minus pi to pi x e j omega, and d omega. So this is to find the inverse Fourier transform of discrete time signal, and this is to find the Fourier transform of a discrete time signal. So Fourier transform describes which frequencies are present in the original function. So whenever you take the Fourier transform, in the end you will have a different frequencies. So by Fourier transform, you can notice that which frequencies, like which number of frequencies are, which harmonics exist in the uh, for original function. So the original signal can be recovered from knowing the Fourier transform. So if you want to recover the original signal, for example, x of n, and you have the Fourier transform x of e j omega, so you can recover the original signal and vice versa. The function x of e j omega is periodic in omega. So periodic in omega, it means that it's in omega domain, it is periodic. It repeats itself. But what will be the period after 2 pi? So 2 pi will be the period and periodic will be in omega domain. So function e j omega is a periodic with period capital N equals to 2 pi for a discrete time case. So x of j omega e j omega and x of we can similarly write in f domain as well. Instead of e j omega, you can write x of f, it's same, right? X of n e minus j 2 pi fn. Let's discuss DTFT derivation here. We have to prove the synthesis equation and the analysis equation. So let's start how to derive that two's equation. So let xn be the aperiodic discrete time signal. This is the aperiodic signal. However, it is a discrete time, right? And aperiodic means that it is not periodically repeating. So it has a period from minus n1. It has a range of values uh, which is positive, like not 0 is from minus n1 to n2. We construct a periodic signal x tilde n for which xn is one period. So we can use, by using this x n aperiodic signal, we can construct x tilde n. It's another signal which is a periodic signal. How it is periodic? It means that we are repeating the xn with uh, taking number of copies, like replicas of the xn with a specified interval, after specified interval. So each replica is centered at an integer multiple of n. So each replica is centered. For example, minus n1 to n2 is the range of this signal, whereas the other portion repeats after n, right, on the positive side, and then again at minus n, and then again at the 2n, and so on. It keeps repeating. So it becomes periodic signal. Consider the following figure which illustrate an example of xn and the construction of x delta n. So these two figures I already mentioned. Clearly xn is defined between minus n1 and n. So you can see that xn is defined between minus 1 n1 to n, right? This n. After that it will repeat. Consequently, n has to be chosen such that n is greater than n1 plus n2 plus 1. So now you have to select the value of n period so that the n1 plus n2 plus 1 should be n should be capital N should be greater than n1 plus n2 plus 1 to avoid the overlaps. For example, if it is repeating, this portion is repeating, so this should be repeated here and here. There should be no overlap here. Clearly, as we let as desired, if, for example, if we consider that n approaches to infinity, this n approaches to infinity, then x tilde n becomes xn. It seems like a continuous type of a signal. So it will repeat. So let us now examine the Fourier series representation of x tilde n, as we consider now it is a periodic signal. So periodic signal, you have a Fourier series, right? For Fourier series, you can for a periodic signal you can represent that signal in terms of a Fourier series. So we already proved that x tilde n equals to summation n. So n is the period, right? For ak e j k 2 pi n over n. We already proved this one in the discrete time Fourier series part as well, where ak is equal to 1 over n summation n x tilde n e minus jk 2 pi n over n. Since x in is defined between minus n1 and n2, right? We already defined. So ak in the above expression simplifies to, instead of capital N, we can change it from minus n1 to n2, as the range we specified is minus n1 to n2, x tilde n e minus j k so on, and equals to 1 over n if we consider that the period is infinity, right? When n equals to n approaches to infinity, then x tilde n approaches to x of n, right? So we can replace this in limit from n equals to minus n1 to n is equal to minus infinity to infinity, and we replace x tilde n by xn, right? And other is rest is same. And where omega is equal to 2 pi over n. Now define the function x e j omega equals to n is equal to minus infinity to infinity x n e minus j omega, and put this in the previous equation which we already derived. So we can see that the coefficients ak are related to x e j omega as this one. So put this in the previous equation. By putting this, you can replace uh, that part with x e j k omega naught, right? And 1 over n is already there. Where omega naught is 2 pi over n is the spacing of the samples in the frequency domain. But it means there are number of samples, so the spacing between each sample will be 2 pi over n. Therefore, x tilde n equals to summation n 1 over n x e j k omega naught e j k omega naught n. And as the period repetition is 2 pi, so we can replace uh, by using omega naught is equal to 2 pi by n, so we can use find n equals to, which will be 2 pi over omega naught, right? So replace the n here with 2 pi by omega naught. So put 2 pi and there will be multiplication of omega naught here. So as n increases, omega naught decreases. We already discussed. And as n approaches to infinity, the above equation becomes integral. So when n approaches infinity, so this equation becomes integral instead of summation. So one important observation is here is that the function is periodic in omega with period 2 pi. Therefore, as n approaches to infinity, x tilde n approaches to xn. So we concluded that after taking Fourier transform, discrete time Fourier transform, the transformed signal will be periodic with period 2 pi. This leads us to the discrete time Fourier transform pairs of equations. So summation is replaced by integral, and here we have a 2 pi. 2 pi means that it can be starting point can be anywhere, but the period will always be 2 pi. For example, 2 if you start from 0, then 0 to 2 pi. If you start from 2 pi, then it will be 2 pi to 4 pi, and so on. And so xn equals to 1 over 2 pi x e j omega n d omega. This is called synthesis equation. And whereas analysis equation is x e j omega n is equal to minus infinity to infinity x n e minus j omega n. This is an analysis equation. Okay, let's take some examples to calculate the Fourier transform. So example 1, consider a signal. You have a given signal xn, a and un, where a should be less than 1. In this case, x e j omega equals to, as we already proved, is minus infinity to infinity. So put instead of x and put this a and un. So a and un, and the general formula e minus j omega. And as you know that unit step is here, so limit changes from 0 to infinity instead of minus infinity to 0. So we change the uh, limit from 0 to infinity. And then a, and because both of e and a both have a power n here, so we can take the n common, we can combine them, so we can write in this way a e minus j omega raised to power n. And we can solve this by taking the formula, which is the sum of the infinite geometric series. You can just check what is the sum of infinite geometric series, so you can just find. So whenever there is a sum of infinite geometric series, it will be equal to 1 over 1 minus r, right? This is general way of writing. And here the r is a e minus j omega. So 1 minus 1 minus a e minus j omega. So this will be the closed form solution for this x e j omega. So the magnitude and the phase are shown in next page in figure 5.4a for alpha greater than 0 and for alpha less than 0. Note that all these functions are periodic in omega with period 2 pi. Let's see how it looks like. Okay, this is the figure 5.4a for the case when a is greater than 0, right? And this is the for the case a less than 0. So we plot the magnitude and phase as well. So you can see that this is the magnitude plot x e j omega, and this bars, it means magnitude. So by taking magnitude, you can see that it is repeating after 2 pi. This is 2 pi period, and this is minus 2 pi. So it will continue repeating. And this is the phase plot minus tangent inverse a over 1 minus a whole square. So by giving with the equation which we found, you can find the exact value by using that equation which we have on the last page. So this is magnitude plot, this is the phase plot. Similarly, magnitude plot and the phase plot for the condition when a is less than 0. You can plot by click and trial or using MATLAB. You can plot these curves exactly over the range. Let's take another example. You have a signal x of n which is discrete time signal, and what is this? Is sigma impulse n sigma n minus 1 plus sigma n plus 1. Then put the find the synthesis analysis equation. Using the analysis equation, you can find the Fourier transform. So which is general equation is n is equal to minus infinity to infinity x of n e minus omega n. So instead of x of n, put all these three terms here, right? These three terms. So by putting this here, we have this equation. So you know that impulse is n means that it is 1 at n equals to 0, n minus 1 it means that it is 1 at n is equal to 1, and it means that n is equal to 1 at it is 1 at n is equal to minus 1. So let's simplify further, write them separately, write three equations, and when you put n equal to 0 here, so it becomes 1, right? And when you put n equals to 1 here, so it becomes e minus j omega. When you put n is equal to minus 1 here, so it becomes e j omega. And just you know that e minus j omega plus e j omega, when you divide, if it is equivalent to 2 cos omega. So we just replace by 2 cos omega plus 1. So this is your solution. The other example, let's take another example. You have to find the x of e omega, where the function given is a n unit step function, which we already, I think, discussed in the previous example as well. So its name a e minus j omega, and by using the infinite geometric series formula, this one, it is equal to 1 over minus 1 minus x or 1 minus r. So you can get 1 minus a e minus j omega. So we can now discuss the Fourier transform of a periodic signal as well. Up to now, we discussed the Fourier transform of a aperiodic signal. Now we will discuss the Fourier transform of a periodic signal. As in the continuous time case, discrete time periodic signal can be incorporated within the framework of discrete time Fourier transform by interpreting the transform of a periodic signal as an impulse train in the frequency domain. So let's take an example. If you have an xn which is e j omega naught n, in continuous time we say that the Fourier transform can be interpreted as an impulse. For example, if you have a e j omega naught, this is the discrete time, this is a continuous time signal. So if you take the Fourier transform of this signal, you will get the impulse at the output. Right? Therefore, we might expect the same type of transform to result for the discrete time signal as well. So for the discrete time signal, we can expect the same as this one. However, the discrete time Fourier transform must be periodic in omega with period 2 pi. As we already discussed, the discrete time Fourier transform is a periodic signal rather than a non-periodic signal. So this suggests that the Fourier transform of this equation should have impulses not only at omega naught but have multiple points like omega naught plus 2 pi, omega naught plus minus 4 pi, so on. So in fact, the Fourier transform is the impulse train. So rather than only one impulse, the Fourier transform of a periodic signal is an impulse train. What does it mean? For example, you can see that x e j omega, it is L is equal to minus infinity to infinity, 2 pi delta omega minus omega naught 2 pi L. So L varies. So for example, if you vary L, L from 0, it becomes one. You will get one impulse, which is 2 pi delta omega minus omega naught. L2, it becomes 2 pi, and so on. So the Fourier transform of a periodic signal Pg omega naught n in this case will look like this. For example, omega at omega naught you have a 2 pi m 2 pi, and then it will repeat periodically after 2 pi interval, because you know that here the period in discrete time Fourier transform is 2 pi. So after 2 pi, then 4 pi and 6 pi, and similarly on the negative side, minus 2 pi, minus 4 pi, so on. Okay, let's take another example to find the Fourier transform of a periodic signal. So consider the periodic signal xn, which is cos omega naught n, and you can write it in this way. We already discussed many times. So where omega naught given here is 2 pi by 5, right? So from equation we can immediately write, because this is the Fourier transform of periodic signal. So we already proved this equation, discussed this equation. So we can break this equation in two parts. Why in two parts? Previously we have a 2 pi here, but now we are writing only pi and pi. So it is two parts, right? Why we are breaking? Because of different sign, minus and positive sign, right? Negative and positive. Because of the two sides of the one side on the positive side and the other is on the negative side. So we can write them separately as well. So it is equivalent to this one. And instead of omega naught, we are putting 2 pi by 5, 2 pi by 5, and other is same minus 2 pi L, because L varies from minus infinity to infinity. However, here we have only two terms, right? So only we have two terms. 2 means A1 term, A1 and A minus 1, or L1 or L minus 1. So when we ever we sorry L0 and um, L0, only one term, which is L0, right? So whenever we put L equal to 0, uh, so it becomes, for example, this term becomes 0 and this term becomes 0 as well. So what we get? Pi delta omega minus 2 pi by 5 plus pi delta omega plus 2 pi by 5, because we don't have any other term, only 0 term, because they have only two coefficient, a0, a minus 0, right? So a0 1 by 2, a minus 0 1 by 2. So and x e j omega repeats periodically with period of 2 pi as illustrated. So this is for L0, whereas as you know that discrete time signal Fourier transform will repeat after a period of 2 pi, right? So look at this. For example, at omega naught, you have this one. So omega naught here is 2 pi by 5, or generally we can write omega naught. So the amplitude here is pi. So pi into omega minus 2 pi by 5. So this delta means impulse. So its shape will look like an impulse. And similarly, after 2 pi, this is centered at 2 pi, because if you repeat after 2 pi, so 2 pi plus omega naught positive side, 2 pi minus omega naught. Similarly, on the negative side of the axis, minus 2 pi, so minus 2 pi plus omega naught, minus 2 pi minus omega naught. So this was the example to discuss the discrete time Fourier transform of a periodic signal cos omega naught. And similarly, for other type of periodic signal, you can use the same equation to find the Fourier transform as well. Thank you for listening, and for Q&A session, we have an online separate session. Thank you very much.